Welcome. This is another video about multivariable derivative. Remember like what we did before, we have like a single variable like f of x, but now we want to see like f of x, y, z time blah blah blah. So this is like multivariable. We have more than one variable. So the objective of this lesson, like in this lesson, in the previous part, we covered the parametric equation. In this part, we will cover partial derivative, and this is a very important concept. So you have like this partial derivative dy over dx. So this part is important for conceptual understanding. And what I want you to understand in this video, the main take home is like the difference between delta y, partial derivative versus like total derivative. Like dy over dx versus partial y over partial x. Yeah. And then another video, we will be doing like implicit differentiation, like parametric equation and implicit differentiation. This is like more math type of thing for just like the FE exam, to cover like this FE exam problem. But this lesson, this is the most important, like this part of the lesson, like partial derivative. That's the most important part of this lesson, because like these two is just for FE exam and like solving problem, but this is important for conceptual understanding, and this will be useful for you later when we get into vector calculus, which you will see like this guys, and when you get to differential equation, partial differential equation, well, you will see a lot of these guys. Yeah. Okay. So let's understand like what is this guy. Yeah. Okay. So let me show you what is this guy. Yeah. So here, let's read what and know what is this guy is. Yeah, a little bit smaller. Yeah. Okay, let's go. So a partial derivative is a function rate of a change with respect to one variable holding other constant. That is basically what it is. So I hold all, so I have a function of x, y, z time. I hold all these constant, and I just see how the function rate is changing with respect to only one variable. So let's see this example. So let's assume you are walking or hiking across this hill, and I want to see like z, that's like my function, like the elevation as a function of x and y. So I want to find like your elevation as a function of x. So that's like x latitude and y like longitude. So how do I do this? So with I can do this with partial derivative. So basically I can hold y constant. So here I can just like, let's say 1. Yeah, so across, so y is not changing, y is 1. Yeah, so y is 1, it's not changing. And then what I can do is that I can see like how z is, like I can see like the rate partial z with respect to partial x holding y constant. Yeah. And let's say if this is a changing in time, that would like maybe like, let's say add time here. So that would be like partial z with respect to partial x holding y and time like constant. Yeah. So you hold like all other variables constant like y and t, and you see how z is changing with respect to x. So like you see here, as I move along x, this is how z is changing. So that is like my height z, and as I move along x, this is, and you can calculate like the rate of a change. So you see here, this is when you rest, like your rate of a change is 0. This is here you have like a positive slope. Here you're sloping down, you have like a negative slope, and so on and so forth. Yeah. But I just did this by holding this guy constant, and that's how I could find like the derivative. That's how I could find my rate of a change. Yeah. Okay, so let's see this like into, let's see another example, like, or let me explain this again. Just repeat, yeah, with an example. So for a function like f of like multiple variable here, partial derivative can be found with respect to one independent variable. We did it here, like with respect to x, yeah. So I found like z with respect to x, treating all other variable constant. So I treated like y and t as constant. Yeah. for example. So here, this is like, it would be kind of geometric interpretation, or if you want to look at this. So I'm giving you here a function. This is, by the way, a function. Like if you look at this guy, that's a function of a sphere. So that's basically a function of a sphere with radius equal to 3. So I'm just plotting here part of the sphere. If I plotted like this whole function, it would look something like this. So that would be like a radius of 3. Yeah, radius of 3, radius of 3, that would be your x, that would be your y, and that would be like your z. But like in the previous figure, I'm just like showing like this part of it, yeah, just like this part. But it's not a very good drawing, yeah. But anyway, doesn't matter. And I'm asking you, like, what is the slope at this point? So at the slope at x is equal to 1, so I move here equal to 1. Y is equal to 2, and z is equal to, like, I move like z is equal to 2, and here y is equal to 2. So at this point, I'm telling you what is the slope at this point. I mean, how can I do something like this? I mean, this is not easy, yeah? So one way to do this is that I can use partial derivative. So I can assume, like, I can say, okay, I will just go at y is equal to 2 at this plane, like plane of constant y, yeah, here. And then I will just assume that y is constant, and I will see basically like here, yeah. I will see how my uh, z is changing with respect to x. So here, this is like my x, and this is, I will see, I'll just get a curve. That's like similar to what we did before. So I will see that how z is changing with respect to x. So like you see this guy, I'm just plotting it here. So that would be like a simple slope like this. Okay. This is basically how. So again, you take a constant plane here, you plot like this curve, and that's just a way to visualize it, yeah. So let's just solve it. So how can I solve something like this? I can just express, I can say like z, yeah, square is equal to 9 minus x square plus y square. I want to find like z as like a function of like, z is here is like a function of x and y. I can say that is equal to 9 minus x square plus y square. Now I want to find like the slope here. So how could I find the slope here? So in order to find the slope here, I can use the concept of partial derivative. Like I can assume that this guy is a constant, just a constant value for this guy, and then basically I find like partial z with respect to partial x. That is the trick. Okay, so here I can say like partial z with respect to partial x. And how do I do this? Yeah. Again, y is treated as a constant. So I mean, this is just like so you remember, like this is equal. Like let me do this for you. Minus x squared plus y squared to the power of half. Yeah. So to find this guy, remember you bring this guy down, so that would be half. Yeah. Time 9x plus y, like everything here, to the power negative half, and then you take the derivative of that thing in between the bracket. Now here is the trick. The derivative of this guy, like between like the bracket, what is the derivative of 9 is 0 here. dz with respect to dx, that is like negative 2x. And what about this? Like dz with respect to x with y squared. That's a constant, so that would be, sorry, here's another minus. Careless mistake. This is the most common mistakes I find when grading exam is like these careless mistakes. Yeah. Okay. And then that would be another 0 because that's a constant. That's the whole idea. Like I just take this as a constant. This is not a changing. This is just a constant. This is just a number which is like equal to 2 or whatever. It's just like a number. Yeah. Could be anything, but it's treated as constant. Then I just uh, I just like, what do I have here? Did I do any other careless mistake? No. I can simplify this, can get rid of this guy, I can get rid of this guy. So I can say like partial z with respect to partial x, that is equal to minus, I guess this minus here, x over square root. I just bring this guy down, 9 minus x square minus y square. Yeah. Now, this become very simple. And this is great because now I can find the rate of a change of z with respect to x. Yeah, I can find like how the surface is changing with respect to x. I have like an equation that describe how z is changing with respect to x, but this equation also has my other variable y here. So if I want to find like the slope at this point, that become like easy. I just like substitute for this point. So I have like my point is like 1, 2, and 2. So that's like my x, y, and z here. So basically I substitute like my x that's equal to 1 square root of like 9, 1 square that's like 1 minus 2, so that is like 2 squares, that's 4. So if I did this, that will give me, oops, if I did this, that will give me like minus 5 minus, so that is square root of 4, that will give me 2. See, I forgot my minus, so I get like minus 2. So the slope here is basically minus 2. See how I was like, from something like this, where they're all mingling together and I cannot solve it, I was able to like separate this here, find z as a function of x and y, make y constant, and then take the partial derivative, and this will be constant, and then I can solve delta z with respect to delta x. Yeah. So here, this is like as a summary of this problem. Let me like delete this and do it again. Yeah. So basically, it's just to recap and to see what we understand so far. So I have like this equation. Yeah. I was able to express z as a function of x and y. Yeah. And then how could I find like the derivative, like the slope at any, like here, the slope like z with respect to x. So basically I can hold y constant and find like partial z with respect to partial x, then I get this equation. So for example, if I told you what is the slope here at the pole, like let's assume this is the earth. So we have like this is the radius 3, this is just for the sake of argument, yeah. This is like an earth or a pole, and this is like your north pole and south pole. So if I told you what is the rate of a change here, you see here, slope here is 0, remember? This is like the slope here would be 0. That's what we expect. Like, will this equation give us 0? I mean, let's try. So here, what is this point? So this point here, I have, so this is like my x, this is my z, and this is my y. So at this point here, what is my x? So my x is equal to 0. What is my y? My y is equal to 3. And what is my z? My z is equal to 0. So, and you see here the slope here is 0. Yeah, that's what I would expect. Yeah, it's flat. The pole is flat. So at the pole, everything will be flat. The earth will be flat or something like this. Yeah. So will I get this? So yeah, this should, so here x is equal to 0. So that's like 0 divided by whatever. That will give me 0. So I got a slope of 0. How about this guy? Like, what is the slope here at this point? Remember, this doesn't look, remember, like when you got these guys here, just like when we were doing optimization, that was called the critical point, and this guy was called the singular point, where like the slope is extremely sharp, like when you have this sharp bridges. So I would expect the slope here to be like uh, the slope here will like align with this tangent, and it would be like infinity or like undefined or something like this. Yeah. Remember, like here, if, like, so this looks like a singular point. So can I do this? So what is this point? Let's do what is this point. So this point, my x is equal to 3, my y is equal to 0, and my z is equal to 0. So let's substitute here and see if we're gonna get like something infinity or undefined, or yeah, like undefined, yeah. undefined. So let's x here, that would be like 3 over square root of like 9 minus 9, yeah, and this is like minus 0. So here I got, what is this, like square root of 0, so here I got like 3 over 0, and 3 over 0, this is like undefined, so derivative cannot be found, and this is exactly what I got here. So this is just like a review of what we did previously. Okay. But anyway, let's just move forward. So this is an FE exam question. Let's see how we are doing in time. Not bad. Yeah. This is like an FE exam question. I'm telling you, find the partial derivative of delta z with respect to delta x. So this is just like an FE exam stuff. So basically what I'm telling you, partial z with respect to partial x. What does this mean? Partial z with respect to partial x, so that will be like 3x squared. Yeah. How about this guy here? So this is 3, this is a constant, this is a constant. So that is basically would be plus 3y squared. Why? Because this is just a constant. Plus, what is this guy? This is a constant, so that be plus 0. And what's this guy? That's a constant, so that's minus 0. So basically, like the final solution will be like 3x squared plus y squared. Very simple, and you get like easy points. So like if you find this in the FE exam, yeah, you easily get these points. Yeah. Here, this is like another thing, partial derivative. So I have this again like FE exam, FE exam. So I have one for the practice and one for the homework. I will solve this in the tutorial. The difference between these two is that like one, I'm asking you what is, read this problem carefully, because I noticed some of you understand the concept, but you didn't get good grades in the homework because you didn't read the question carefully. So please read these questions carefully. Here is telling you, like for the practice problem, is telling you partial g with respect to partial v. Yeah. And the homework is telling you partial g with respect to partial u. So that would be different. Yeah. So wait, I will solve this in the tutorial if you want to see this. So that's the solution. Like try to solve this one on your own. Like try to solve like this practice problem on your own. Like pause this video and try to solve it, and then you can check the solution here. Yeah. Now let's move to an important subject, because here I just want to show you like the difference between the total derivative and partial derivative. Uh, so So here, like converting to partial derivative isolates the rate of a change with respect to one independent value holding other constant. So if I have like a total derivative, like dy over dx, how could I convert this guy to like partial derivative, like and write like an equation for this? Yeah. So here, suppose we have a function, like so this function, we suppose x as a function of t, for example, and y as a function of t that are function of t. So I have f of x is a function of t and y is a function of t. Then the total derivative with respect to t can be expressed, so I can say like, let me just delete this guy. Yeah, here. I can just express like that's the total derivative, df with respect to dt, something like this, okay? The total derivative with respect to t can express in the term of partial derivative with respect to like this guy, and sorry, here this is y. Yeah, this is a mistake. Sorry, like you'll find a lot of these typing mistakes because this is teaching this course for the first time. That's not unexpected. That can I edit it here even? Let me see if I can. Even if this equation is editable. No, I cannot edit it here. But anyway, doesn't matter. Just know that this is wrong. This is like y of t. Okay, here we go. Since f depends like on t indirectly, so f it depends on t, but indirectly it depends on t through like x, and it depends on t through y. We can like use the chain rule to find the total derivative with respect to t. So basically, like I can, this is one of the rules of calculus, like similar to the other rules of calculus we used before, and this is like another rule that's based on chain rule. So I can basically say this like the partial derivative of my function with respect to x times the total derivative of x with respect to t, yeah, plus the partial derivative of my function with respect to y times the total derivative with respect to t. Again, what we are seeing here, this is basically just like the chain rule, because this guy cancels with this guy, then I will get f to the delta t. So because like see, this is just like this is the chain rule, yeah. If I cancel this guy with this guy, I'll get partial f with dt and partial f with dt. And but why do we have like two of them here? Because remember, partial derivative, this is the contribution from x, and this is the contribution from y. So you have to add them, and that would be your total derivative. What does this mean? Like, so for example, like let's say you have volume here, yeah, and yeah, let's say, and then you have like contaminants that is entering through here, yeah, and contaminants that's leaving from here. So that's like the x direction. But you could also have a contaminant that's like entering from here and like leaving from here. That's like your y direction. You can have similarly from z direction, something is entering from here and something is leaving from here. So what would be your total flux? So your total flux basically is what is not just from the x direction. You have flux from the x direction, you have flux from the y direction, you have flux from the z direction. And that's why you need to add them. You need to like the what is entering from the x direction, what is entering from the y direction, what's entering from the z direction. That would be the total things that is like entering to my system. Similarly, the total things that is leaving to my system. And that's why you can add like your partial derivative, because in partial derivative I'm just looking, okay, what's happening through x, what's happening through y, what's happening through z. That's exactly what I'm looking for. Versus total derivative, I'm looking at the system as a whole, like what is happening through x, y, z as a whole. I don't know if this makes sense, but this is basically like the idea of like total derivative and partial derivative. So basically you can express like a total derivative as partial derivative, and that will tell you so here what is happening along each dimension, here what is happening along all my system, or like all dimensions or all my variables, something like this. Okay. So here, I mean, this is just like an example. So convert the total derivative to partial derivative. So basically, to solve like for an intermediate variable. So here I have like an f of x function of x and y. So x is equal to this with so x as a function of t is equal like to t squared. Y as a function of t is equal to t plus 1. And then I'm telling you find the df of like x, yeah, x and y with respect to like dt. So how can you do this? Basically, that's like how you do it. Like, so you find the partial derivative of x with respect to x. So this is easy. So df with respect to dx. Do you remember how to do this? So that would be like 2x. Y here is a constant, so that would be plus y. And then you find like df with respect to partial, sorry, not the partial f with respect to partial x. That would be what? So that is a constant, so that would be 0 plus y here plus x, yeah? So that's basically what you do it. And then, so, right, write this down here, and then you find like dx with respect to dt, dx with respect to dt, so that would be like 2t, and then you find like dy with respect to dt, and that would be like, this is 0, that would be 1. So, and then you just put everything together, yeah? So here, uh, like how to find like the derivative of this guy, that would be like partial f dx, so that's like 2x plus y, yeah, dx over dt, which is like 2t, okay, plus partial, where is this way? I did a mistake here, sorry. This is with respect to y, yeah, plus partial f was like plus x times dy to dt plus, so that's just like plus x times 1, yeah, here. So if you did this, you can basically like multiply this here. I mean, if you want to simplify it, so that would be uh, now here, I mean, I don't want x, I want like everything would be like with respect to t. So I can just like here substitute. So I can say like x, I can substitute x, that's like t squared plus y. So I can substitute y, that is like t plus 1. Yeah. And that all will be multiplied by like 2t plus x. I can substitute x with like t squared. So I can express everything as t squared. Yeah. So here basically that's this. It's like something like this. Yeah. Because we don't need. So you can just like extend this. Like, so if you extended this, that will give you what, like 4t plus 3t squared plus 2t, yeah, something like this. Yeah. Then you can take like a t as a common factor or whatever. Yeah. But anyway, so that's basically like what we learned here. Like we learned how to basically find the, like use the concept of partial derivative to solve like a problem like this. Yeah. So here, like again, like total derivative, partial derivative, parametric equation, and the chain rule. So here I just want to like combine like all these concepts together. Like I just came up with an example where I could like just combine like all these courses, all these concepts for you together so that you can visualize these concept, yeah. So here, for example, like a man climbed a mountain in an ZX profile according to this parametric equation. So I'm giving you like two parametric equation. So that is like x as a function of time. So this would be my x position as a function of time, and this would be my z position as a function of time. At the same time, the temperature at a point, so the temperature at x and z in the plane is given by a function of, so here, this is like I have a temperature is a function of also x and z. So I'm like climbing a mountain like this, yeah. Okay, and my that's like my x, and, and that is that would be like my as a function of time. Uh, that would be like my, so I'm climbing a mountain like this at a function of time, like I have to draw this like in 3D as a function of time. That would be my x and z location, yeah, as a function of time. And then similarly, as a function of space, the temperature is changing, and the temperature is given by my where I am in x and where I am in elevation. Yeah. So basically, find the rate of a change of temperature experienced by the man with respect to time and when t is equal to 2. So at time 2, what is the temperature that this man is experiencing? Yeah, and then generally it's asking you to find the rate of a change of temperature with respect to time. So it's asking you to find like dt temperature with respect to d time, and then like use this to find uh, the rate of a change at t is equal to 2. So basically, like how can I do this? I just basically, so this is an example of total derivatives and how where I can use like parametric equation and like partial derivatives. So basically, temperature, let me just explain this because this example will help you to see these concepts. So temperature is a changing with time. Yeah, that's basically what it is. Uh, but this time is like temperature, sorry, I, like temperature is a changing with like respect to x and y. Yeah. And this x and y is changing with respect to time because I have like x, that's like a function of time, like my location, and my, let's say z here, yeah, x, my z is also a function of time. Like my x and z locations, these are also a function of time. So basically, I'm looking here like t, I have a relationship between like temperature and location, but I know that my location is changing with time. So I want to find like how the temperature is, like the temperature that this man is experiencing, how it will change with time. So the man will be like cold here, would be warmer here, would be warmer here, would be cold here, would be cold here, would be cold here, depending on his like location, depending on like the time, and time is changing with location. So how could I do this? So here I have a relationship between x and z, yeah, and x is a function of time and z is a function of time. So I can basically express like my total derivative, which is how all these things are changing. X temperature is changing with x, y, z, and t with partial derivative. Uh, So I can basically like say partial t over partial x, that is equal to delta x over delta t plus partial t with y, that is equal to dy with respect to dt. Yeah. So here I'm converting like my total derivative to partial derivative, and then that becomes like trivial, like to solve something like this. So like to solve something like this, partial t with respect to x, that's equal to what? So here that's like would be 2x. Again, this is like a constant minus x, yeah, and this partial t with respect to partial y or partial z, sorry, there's no y here, it's all z, like with respect to partial z. So that would be like 0 here, that would be 4z, and that would be minus x, yeah, because this is like a constant. And then I just find partial x with delta x with respect to delta t. That would be here, that would be 3t squared minus 3, and then delta y with respect to delta t, and that would be 2t minus 2, something like this, yeah. And then you just like substitute here. So if I did everything correctly, I think let me just check, and you just like substitute uh, uh, you just like substitute like everything here, and then you can you will have an equation that should look something. I mean, I can substitute it, but let's see how we are doing in time because I don't want to keep this long. Ah, I think we are doing good in time. Yeah. So I can basically substitute here 2x 2 see, this is like x. Sorry, that's like this will give me here x, and so basically I have x dx time like 3t minus 3, yeah, plus d, sorry, this is z, yeah, I have here like 4z minus x time dz over dt. So here that would be like 2 times t minus 1. Yeah, something like this. That be my total derivative. So basically, what does this mean? So you see here, this very actually this looks interesting because here I'm saying like the change of, sorry, this is my, the change of temperature with respect to time. This is a function of my x position. This is a function of my z position, and this is also a function of time. Yeah, like which is, so I have this. I can just like express everything as a function of time because I know that x is equal to this, so I can basically like substitute here x for this guy here. I can substitute z for this guy here, and then have like everything in terms of time, or even like simpler, and instead like, you know what's an easy way of doing this? I can just like find like, okay, I can find like substitute like, because I want to find like a t is equal to 2, so I can just put like t here is equal to 2, so that would be like 8, that would be 6 as minus 2, so that would be like a t equal to 2, like x of 2, that would be equal to what? 2, yeah, because like 8, that would be equal to 2, and then here z2, that would be uh, equal to what? So that's like 4 minus, so that would be equal to 0. So that's, see, that's like kind of, so x, so here that would be like 2 times 3 to the power, I mean, I can, yeah, 3 to the power minus 3 plus my z here is equal to 0, and so that is like, I have a negative here, so, and my x is equal to 2, so that is will be like negative 4 t minus 1. Yeah. So now I substitute t is equal to 2, so that would be like 3, yeah, times 4 minus 3 minus 4 and 2 minus 1. So if I did this, if I did everything correctly here, so I have like, this is 12, so minus 3, this is 9, so here I have like 18, and I have minus, did I do something correct here? Let's see, t is equal to 2, yeah, so that's minus 3. I think I did, so I have 12 minus 3, that's 9 times 2. What did I do here? Uh, so delta t with respect to delta x, like, did I do this guy correct? So here, oops, delta t with respect to delta x. So this is like 2x, yeah, minus x. So that will give me an x. So yes or no? Sorry, I did a mistake here. This is minus x. So here I did a mistake here. So delta t over delta x, that would be, because I have an x here, I didn't see this z, so this should be minus z, yeah? And delta t with respect to delta z, that should be 4z and minus x, yeah. So that's, I think that's the mistake that I did here. So like, so z is equal to 0 at 2, yeah. So z at 2 is equal to 0. So here I have 2x, so that should be 4, and here, so that should be 4. And what do I have here? That should be, I have a mistake here. So that would be 9, yeah, times 4. So I have like 4 times 9. And here I have minus 4, yeah. So that 4 times 9, that is like 36 minus 4, then I got like 32. So that's like the answers that I get here. Yeah. Something like this. So basically this is that, like, just try to like think about it and see like how I'm expressing here, like this is my total derivative and this is like my partial derivative. I'm expressing it. Yeah. Something like this. Okay. So here, this is like a practice problem. I will solve this in the practice problem session. And this is like the homework problem. So let's look at your homework problem. So your homework problem, length of a rectangle is increasing at a rate of this. So I'm already giving you the rate, yeah? The delta L over delta T, centimeter per second. And its width is increasing at a rate of, so I'm also giving you how the width is increasing. The area of the rectangle is given by, so area is a function of length and width, and length is a function of time, and width is a function of time. So you can think of this as anything that's increasing, like a plume, for example, that is increasing, fire that is increasing, uh, anything, yeah, that is like increasing with time, yeah. Okay, so here this is, and L is a function of time, the width is a function of time, and then the area basically is length time width, so the area would be a function of time. So find the rate of change of the area of the rectangle. Is it changing when the length is, so I'm giving you like when the L is this and when the W is this. So, and I'm telling you like find this guy at L is equal to 10 and W is equal to something like this. So how do you solve this? We know dA over dt over uh, partial t, sorry, not t, sorry, partial a, like how a is changing with respect to L, yeah, and then delta L with sorry, delta L with respect to delta t plus partial a with respect to partial w, and then how w is changing with respect to t. Yeah. So basically, uh, this is like how we can solve something like this. So are we giving, so this already, like this guy here is giving to us, yeah? This guy here is giving to us. So what we want to find like this guy, yeah, and this guy. So so this is my equation. Like I have area is equal to LW, and I want to find partial area with respect to L, yeah, and then partial W, sorry, partial area with respect to W. So that's basically what you need to find. After you find this guy, you substitute this guy here. You substitute this guy here, and then you are done. And remember, like you know how to find like this departure for this guy here. Yeah. Remember? I mean, you know this. Yeah. This is like, I mean, we did this before. Like if I'm telling you like z is equal to 2xy square, yeah, and I told you find like departure z with respect to x. So z would be like 2y square, and if I told you departure z with respect to y, so that would be like 2 times 2, so that would be like 4xy. Yeah, because this is constant and this is constant, and then that's how you do it. Okay, so I think that's all for this lesson. How are we doing in time? I mean, not bad. So I will stop here and see